So I think we are live now, right? So hello and good morning to all. I am Ridul Ghosh, head of the department in Computer Science, Shyampur Siddheswari Mahavidyalaya. Would like to welcome to all the participants, my colleagues and the speakers, Mr. Abhijit Vishwas and Dr. Vikramaditya Sahu, in our international webinar entitled Recent Trends in Mathematics and its Application in Computer Science, which is jointly organized by the Departments of Mathematics and Computer Science in association with IQAC, Shyampur Siddheswari Mahavidyalaya. We will start our program by the welcome speech of our Honorable Principal Sir, Dr. S.K. Bose. But due to some reasons, he is unable to come live, but he has sent us his warm greetings.
Good morning, everybody. First of all, I welcome all the participants in the international webinar on recent trends in mathematics and its applications in computer science, being organized by the Department of Mathematics and Computer Science in association with Internal Quality Assurance Cell of our college. I would like to convey thanks to the speakers of this webinar, Dr. Vikramaditya Sahu, Assistant Professor, Department of Mathematics, NIT, Rourkela, Odisha, and Mr. Abhijit Vishwas, Research Assistant, Department of Mathematics, Temple University, Pennsylvania, USA. And they will deliver their valuable lectures in this webinar. I would also like to convey thanks to the coordinator and members of the Internal Quality Assurance Cell, along with the teachers of the Department of Mathematics and Computer Science of our college, who deserve it for arranging such a webinar in this time of pandemic. I think the participants will be benefited from this webinar. I expect a grand success of this webinar. Thank you all once again.
For your valuable speech. Now, I would like to welcome our dearest IQAC coordinator, Sri Rajosi Mukherjee, to say a few words.
A warm welcome to all the resource persons who have joined in this international webinar from different parts of the globe. And a very warm welcome to all the participants who have taken the pain to log in on a comfortable Sunday morning to attend the webinar, which is being organized by the Departments of Mathematics and Computer Science. In this critical situation, all of us are experiencing something that we have never experienced before. And as academicians, we are constantly searching for means to deal with this extraordinary situation. In pursuing these lines, Shyampur Siddheswari Mahavidyalaya has been organizing a string of webinars on different topics organized by different departments. On behalf of the IQAC cell of Shyampur Siddheswari Mahavidyalaya, I should like to thank our principal and mentor, Dr. S.K. Bose, without whose moral support these efforts would never have been possible. I shall also like to thank the governing body members who have constantly encouraged us to go ahead with our effort. I'm sure all the participants and us will be benefited by the valuable lectures of our esteemed resource persons. So welcome all of you once again, and I shall now like to welcome Dr. Arun Kumar Maiti, the head of the Department of Mathematics, to deliver his welcome note. Thank you very, very much.
Good morning, everybody. We have been going through a pandemic situation due to COVID-19 for the last 4 months. In this situation, we are all confined to our household. Keeping the spirit in mind, we, the Department of Mathematics and Computer Science, in association with IQAC of Shyampur Siddheswari Mahavidyalaya, have jointly organized an international webinar entitled Recent Trends in Mathematics and its Applications in Computer Science. On behalf of our department, I welcome all the participants in this webinar. I also thank to the honorable speakers who have consented to deliver their speech in this webinar. Such type of webinar would not have been possible without the moral and active support of our honorable principal, Dr. S.K. Bose, and the honorable members of IQAC and also the honorable members of governing body. I convey my sincere gratitude to the honorable principal, Dr. S.K. Bose, and the honorable members of IQAC and also the honorable members of governing body. Now I request Professor Mridul Ghosh, Head of the Department of Computer Science, to introduce the first speaker in this webinar. Thank you. Thank you all.
I would like to share a few words for our participants. I request all the participants to install the Telegram app, which is given in the brochure, or you may download it from the Play Store and join in our Telegram group by the link given in the brochure. All further details will be shared on that group only. After this webinar, we will share a feedback link. Please fill up this form carefully with your correct details. Based on the details, certificate will be generated. The feedback link will be active for 10 July, tomorrow, 12 p.m. If you don't put feedback, you won't get any certificate. For certificate to download, we will give you another link after 10 July. So now I would like to introduce our first speaker, Mr. Abhijit Vishwas. Mr. Abhijit Vishwas completed his graduation from Ramakrishna Mission Vidya Mandir, Belur Math in Mathematics Honours. After graduation, he completed his Masters in Mathematics from IIT Bombay. Then he served as a teaching assistant in IIT Bombay for a year. In the last few years, Mr. Vishwas has been working as a research assistant in Temple University, Pennsylvania, USA. His research interest is mainly focused on numerical methods for partial differential equations, hyperbolic conservation laws, and numerical analysis. Today, he is going to talk about the geometric view of first order ordinary differential equations, and if time permits, he will also demonstrate some of his research problems currently he is working on. So may I welcome Mr. Abhijit Vishwas.
Thank you. Good morning to all. Thank you, Mr. Mridul Ghosh, for kind introduction. I appreciate that. Thank you, Dr. Arun Kumar Maiti, the head of the department and the organizing committee, for inviting me to give a talk in this prestigious webinar. And this is the first time I'm gonna give a talk in a college, so I'm really glad. I want to especially thank to my friend Aniruddha and Deepshika, who got me in touch to this and to make this talk happening. So as you know, like Mr. Mridul Ghosh said, I'm going to talk about geometric view of first order ODEs. If you are in second year or third year, you already know how to solve first order ODEs analytically, but I'm going to show you a different perspective, like geometric view of ODEs. And I hope you will learn something new today. And if not, it doesn't hurt to learn things twice. So let's get started. Let me just share my screen. Okay. So I hope you guys can see my screen now. Okay. So The topic is geometric view of first order ODEs. The most general form of first order ODEs can be written as a function f, which is a variable like function of three variables, x, y, and y prime. Now, x is the independent variable, y is the dependent variable, and y prime, that's the derivative of y. Of course, this is a very complicated equation because it can involve these three variables in a very complicated manner. So this is very difficult to solve. So that's why we consider the standard form, which says y prime equal to f of xy. Now, this is not possible always. Basically, you cannot separate y prime from x and y. But let's assume for this talk that we can do that, and we have this kind of ordinary differential equation. In addition to this, if we have y of x naught equal to y naught, basically if you have some initial value specified, then you call this ODE 1 or 2 with this condition called as initial value problems. I hope you are familiar with this. And we want to solve this problem. So let's see some example. Here are some basic examples. You can see y prime equal to minus x over y. This is a very simple looking first order ODEs, right? You can solve this analytically by using separation of variable, or by other type of methods you have learned in your second year or third year. Then you can see the second equation, which is y prime equal to 1 plus x minus y. This one you can solve by using integrating factor. And all these other simple looking ODEs you can solve by using some analytical methods, and those are not very hard to solve these equations. But my perspective is like how to solve this without solving it analytically. So there is a method, like it's called geometric view, and you can actually solve this equation without solving analytically. So let's see how. As I said, like you can solve this equation in two ways. One is analytical way and geometric view. So let's talk about the analytical views, like which you know already. So if you have an equation y prime equal to f of x comma y, the solution, it's some curve, right? Let's say capital Y of x. It's a curve which satisfies this equation. So if you just plug this into the differential equation, then it must be satisfied by that function. So the solution to this equation is just finding a function capital Y of x such that capital of y prime of x equal to f of x comma y of x. This we know from our course in ODE or course in PDs. Now, what does this correspond to, like each of this? So in the geometric view, you have this f of xy. This gives you direction field. And I will talk about this in a minute. What is the direction field of a differential equation? And then the second thing is this capital Y of x, which are known as integral curve. I'll explain these things in my talk. Like this is the main theme of my talk. So let's first talk about the direction field. So as you can see, this is the definition of direction field. The direction field or slope field of a differential equation is the rectangular grid of tangential line segments that pass through partial solution at that point on the grid. It looks difficult, but I'll explain that. So let me just switch my screen to a notebook. So I'm just gonna define what is a direction field. As you have seen, f of x comma y, right? That's my function. So what is this basically? This is my equation, right? What this equation is saying that the solution curve y, it has derivative which is equal to f of x comma y at every point x comma y. So if you draw this on a coordinate plane, right? This is your x, this is your y. And if you take any point, like let's say x comma y, and if you just calculate this f of xy, so this is a function, right? Uniquely defined function at each and every point x comma y. So given a point x comma y, if you calculate f of xy, that will give you some value. Let's call this as m, okay? And m is a slope. So if you have a slope, then you can draw a little line element, right? And how do you get this? This is the line which makes the angle theta with the positive x-axis, given by tan theta equal to m, right? So we all know this fact. So now you can do these things for all possible points in this plane. So if I take a bunch of points here, and if I just draw this thing, I mean, this is just given by this little line segments are defined by this function f of xy. So you can just draw a bunch of lines here. Let's say, so this is like this is filled with all these little line segments in this plane. Okay, so I'll get tired very soon, so I'll not draw more than this. Okay, so basically direction field is a field which has a vector assigned at each and every point in this plane. Okay, and I'll just explain that integral curve. What is an integral curve? An integral curve is a curve which is tangent to each of these line segments. So for example, if I just take, let me use a different color. If I take this little curve, look at this. This is not appropriate, but still you can see that this little line segments, they are kind of directing this line in a direction in such a way like it's a curve, right? And this curve is known as integral curve. Okay, so there's direction field, there is integral curve, and we have now a theorem, or okay, let me just switch. Okay, so what is the direction field, right? Now let me just go back to my slides and let us talk about how to draw a direction field. I have already shown you once. So there are two ways. What computer does, so there are two ways. One is a computer way and one is human way. What computer does is like it takes uniform grid, like I just draw in, I just drew in my notepad, right? It takes uniform grid in a domain, and at each point of that domain, it computes the slope and it just puts the little line elements. Okay, so this is how a computer computes the directional like field, and it just puts this little line segments. And the human way is a little different because we are smarter than computers. So what we do, we first pick a slope. So let's say we pick slope equal to 1, and we try to find the solution or the curve f of x comma y satisfying f of x comma y equal to c. And that will be a level curve, and at each point of that level curve, the slope will be c. Okay, and this little this equation, what we get as level curve, it's called isoclines. So at every point of an isocline, you will get the same slope. I'll also explain these things in a minute. And of course, I defined also integral curve. An integral curve is a curve that goes through the plane, and at every point, it tangents to the line elements. Okay. And we have this equivalence theorem. Now the theorem says y of x is a solution to y prime of x equal to f of xy if and only if the graph of yx is an integral curve to the direction field. Okay, so this is a theorem. So if you want to solve this equation y prime equal to f of x comma y, all you need to do, you need to draw a direction field, and then once you draw the direction field, then you will see how the integral curves look, and you can just easily draw those, and that's your solution. And the proof of theorem is very easy. You just have to write down what each of these sides really means. So if you take the left-hand side, which is y prime equal to f of xy, and we already know a capital Y of x is a solution to this equation if this satisfies the ODE. That means y prime of x equal to f of x comma y of x at these points. This is the left-hand side, like this one. And what does it mean to be an integral curve to a direction field? It says the slope of y of x, that's by definition, right? By the definition of integral curve. The slope of y of x is equal to slope of the direction field at x comma y of x, which is basically, if you just write down slope of y comma x is just y prime of x, and the slope of the direction field at x comma y of x is just f of x comma y of x. Okay, so this is very easy to see, like these two things are equivalent. So solving a differential equation analytically is same as drawing the direction field and get the integral curves. Okay, so this is our theory. Of course, now this is a little technical, but I'm going to show you all these things by using examples. So our first example, which is a very basic example, which is y prime equal to minus x over y, and we definitely know how to solve this. But let's solve this using this geometrical view. Okay. So let me draw these things. Y prime equal to minus x over y, right? So this is our given equation. Now, by the standard form, we know that our f of x comma y equal to minus x over y. Okay. As we said, if you give it to the computer, it will just take, a bunch of grid points, like uniform grid points in this plane, and at each point, computer will compute the function f of x comma y, and it will put little line elements. And I'll show the computer way using some software. But before that, let me show you how human does it, like how we do it actually. So as we said, we pick a slope first, c. Okay, and we solve this equation. So if my x over y equal to c, then y equal to minus 1 over c comma x, right? So this is our isoclines. And we know at each point of this isoclines, the slope is c, because that's how we chose this slope c, right? So let me just choose a bunch of c's. Let me just choose c equal to, let's say, minus 1 first, okay? So if I choose c equal to minus 1, then my isoclines becomes c equal y equal to x, right? That means, let me just draw this first. Y equal to x is just this line, right? So this is my isocline. And I know at each point on this isocline, the slope is minus 1. And that means at each point of this line, I have slope minus 1, and minus 1 is directing in that way, right? So I can just put little line elements, which is directing to minus 1. Okay. I hope this is clear. Let me draw a bunch of these numbers. Okay. So now let me just take c equal to 1. Okay. Yes. So, yeah, I'm sorry for the interruption. Okay, sorry. So if you take c equal to 1, then your isocline becomes y equal to minus x. And as you can see, this line has slope minus 1 over c. And the slope c, that means c times minus 1 over c is always going to be minus 1, right? So if you have two line elements, like one is the isocline and one is the little line elements, and their slopes, if you multiply, you get minus 1. That means they're going to be always perpendicular. So no matter what isocline you draw, you always get this little line elements perpendicular to that isocline. Okay. So for c equal to 1, you get y equal to minus 1. Sorry, minus x. So you get this line, and I know at each of this, like each of the point has little line elements, which is slope 1. So this will direct in this direction because I have slope 1. Okay. Now I can choose c equal to 2. I'll c equal to 2 or c equal to minus 2. I'll get lines here, and I know my line elements are going to be perpendicular to this. I can draw many more. And this is also an isocline. I can do that. And the line elements are going to be perpendicular to this. Similarly, this is also an isocline, and the line elements are going to be perpendicular to this isocline. And you can fill this whole plane by drawing isoclines and little line elements. Now, as I said, the integral curves, which are going to be the solution to this differential equation, are the tangent to this little line elements. And you can see, basically this is directing like in this way, right? So if I just, so the like the integral curves are going to be this circles, because at each of these points we have this little line elements which is directing. Basically, this little line elements, they are guiding this integral curve. And if you solve this equation y prime equal to minus x over y, then you get dy. So y dy equal to minus x dx, and if you integrate, then you can just easily solve that c squared or something for some c. So now, of course, if you have initial value problem, then of course you take y equal to, let's say, the positive part, right? And then you get c squared minus x squared. So in that case, your solution will be just this, passing through the initial value which you would specify here. So analytically, we can verify that the solutions are just this upper half, like the circle. And geometrically also, you can see that drawing the direction field and the isoclines and the little line elements can give you integral curves, and those are exactly the solution of this differential equation. So that's basically the geometric view of a differential equation. Okay. So I know my writing and drawing, this is a little sloppy. So I'm going to use a software developed by MIT. I mean, that was a project. So I'm going to use that. I'm going to show you how these things look. Okay. So here you can see my y prime equal to ax over y, and my a is just let me choose this as -1. First, let me show you, and this y prime equal to m, that means the f of xy equal to m. This is the slope which was seen in my notebook. If you choose, let's say, c equal to 1, or c equal to -1 first, let's say, then you know that my isocline is y equal to x, right? Which is exactly this. And my little line elements, these are directing perpendicular to this line. Now you can choose a bunch of isoclines. For example, if you choose c equal to 2, or c equal to -2, c equal to -3, or you can choose c equal to 1, c equal to 2, 3. Right? Now you can see this little, but you can also, I think, click here, and you can see the solution. So basically, this is a solution passing through any of these points on this integral curve. And it does make sense that, look at this. This integral curve has this little line elements which are tangent, and if you fill this whole plane by these isoclines and the little line elements, you'll be able to see that all these points are tangent to these curves. Okay, so this is how you get the integral curve. Okay, now of course, if I just let me just clear all, and let me just show you the direction field. So in a computer way, computer does in a different way. So if you just, so computer selects all the points like uniform grids on this little plane, like from -4 to 4, and it chooses some grids, and it computes the slope, and it just draws the little line elements, and this is how it does. Okay, so at each point it just draws like this little line elements. So now if you just want to click at, let's say, at this point, or your initial value, it's here, basically y of x equal to 0.64 in this case, you can see from here, right? And then if you just click on that, you get the integral curve, and this is basically solution. So this is basically one parameter family of solution, right? As we know, for this different c's, you get different solutions. I hope this is very clear from the picture and all. Now let me do one more example, which is going to be very important to our next theorem, which is called existence and uniqueness theorem for ODEs. And the example goes like this. So y prime equal to 1 plus x minus y. Okay, this is a very simple looking ODE, and you can solve using method of integrating factors. Now, I want to solve this by using this geometric view. So first, let me call this function f of xy equal to 1 plus x minus y. And I know I'm going to make this equal to some slope c or m, whatever you call. Then my isoclines becomes y equal to x plus 1 minus c. Okay. So these are my isoclines. And at all the points on my isocline has slope, like they have slope c. Okay. Now I'm gonna just draw same thing. So if I put c equal to, let's say, 0, then my isocline becomes y equal to x plus 1, right? And at all the points on this isocline, they have slope c equal to 0. So y equal to x plus 1 is just this line. So this is a line passing through 0, 1, and at all the points on this isocline, they have slope c equal to 0. And c equal to 0 is just like, you know, the parallel line segments, right? Because that we know for sure. If I put c equal to, let's say, 1, then I get y equal to x. This is the line which is parallel to this, but slope having 1. And c equal to 1 is just, oh, this is interesting, right? So this is c equal to 0, and this is c equal to 1. This isocline has little line elements in this direction only, right? Because my c equal to 1, that means is tan theta is 40, like theta is 45 degree, right? Which is kind of merging. Okay, now what about c equal to, let's say, minus 1? C equal to minus 1 will give me y equal to x plus 2. And so x plus 2 will be somewhere here, right? And let me choose one more. C equal to, let's say, 2. And sorry, this is c equal to 2. And you get y equal to x minus 1, and that will go through here, right? And I'll have this parallel line. I should have used different color, but never mind. Let me just use different color here. So at this isocline, which corresponds to y equal to x minus 1, has slope 2, right? Slope 2 is a little bigger than slope 1. So slope 1 is this, so slope 2 will be something like this, right? So we can just draw all these little line elements. And here, you know, the slope is minus 1, right? So minus 1 is in this way. And, you know, if you keep drawing this isoclines, like you will get the parallel isoclines, and you will keep getting this kind of thing. Okay. Now, what is happening now? You can already know, like you already know the shape of the integral curve, right? So if you just draw an integral curve, it will go something like this, and it will try to converge or try to merge to this, you know, this isocline, which is very special. Let me write down y equal to x. And from here, you can also see, like, you know, this little line elements, they're kind of directing towards this. So now if you, you know, if you want to draw more, you can see the integral curves, they are like kind of, they look like this. Okay. Now, this is a very important example, and this will illustrate a few things about first order ODEs. Let me first check that this y equal to x, this is a solution. This is also isocline. This has also slope same as c. And you can easily verify that y equal to x also satisfies this. And the other integral curve will have different solution. You can just solve and you can verify that they will exactly look like this. Okay. There are two very important things out of this example. One is, look at these integral curves. I know the behavior here, but do they like really merge to this? And the answer is no. Okay, because the first thing, even before the first thing, any integral curve which is close to this line y equal to x, they cannot escape. What I mean by that, that means they cannot just go to in this direction, because at all these points, this slope are directing towards this y equal to x. Okay, so there is no escape possible once you are very close to this. So basically, they are approaching asymptotically to this particular solution y equal to x. So that is the first thing. Second thing, two integral curves, they cannot cross. And why that? The reason is, so let's say if you have one integral curve is this and another integral curve is this, right? Look at the crossing points. Here you will have slope this, and there you will have slope this, right? So basically at one point you will have two slopes, and that is not allowed, right? Because I know my function f of x comma y, this is uniquely determined, like that uniquely determines the slope at a particular point. So this is not possible. Even touching is also not possible. That means like this curve cannot touch this. So what I mean by that, they cannot even touch, like they cannot be tangent, and this is also not possible. And the reason behind this is something called existence and uniqueness theorem of PDEs, which is very important, because in reality we are interested in well-posed problem, and for well-posedness we need existence, uniqueness, and continuous dependence. So this leads to the theorem, which is called, I think you learned this in second year or third year, called existence and uniqueness theorem. So let me go back to my slides again. So as I said, solution cannot escape from the stable solution, which is y equal to x, as I demonstrated already. And then I said two integral curves cannot cross by an angle for the same reason above. And two integral curves cannot touch. Okay, and this leads to the theorem, something called existence and uniqueness theorem. Okay, so we are basically interested in existence and uniqueness theorem because before we solve the differential equation, we want to know whether a solution exists or is that unique. And this theorem guarantees that under some assumptions, of course, every theorem has some hypothesis. Under some assumptions, this theorem guarantees the existence and uniqueness. Namely, if the function f and the partial derivative of f with respect to y are continuous, then you can guarantee existence and uniqueness of the solution locally around like x naught. Okay, so this is very important. So this gives you the local existence and uniqueness. Of course, the proof is beyond our scope here, but let me just tell you, the proof can be done by something called peak-out iteration. So the existence is given by peak-out iteration, and uniqueness you can prove by following Grunwald's inequality. If you are interested, you can just look into Google or Wikipedia and you will see. Okay, this is not hard. But the main point here is you need two things, f and del f del y, they are continuous. So the existence of a solution is guaranteed by the continuity of the function f, and del f del y being continuous gives you uniqueness. Now, this condition are just sufficient, they are not necessary. Okay, so this is a very strong statement that they are just sufficient, not necessary. Let me explain that, what I mean by this, like why these things are sufficient, not necessary. So in order to understand that, you have to consider this example, which is xy prime equal to y minus 1. Let me just quickly check how am I doing on time. Okay. So let me go back to my notepad and let us just see x y prime equal to y minus 1. Okay, and this is a very simple ODE, right? And we can solve this very easily by separating variables. So dy over y minus 1 equal to dx over x, right? If we are just separating variables, then integrate and you will get some integral. Okay, so let me just do that. Log of absolute value of y minus 1, and if you just take log of c, then you basically get y equal to 1 plus cx. I'm just avoiding this absolute value. We can talk about this later, but let's just concentrate on this thing. So what are the family, like what is the family of solution here? It's just a straight line which is passing through 0, 1 with any slope c, because that c depends on the initial value we specify, right? So let me draw this and then ask the existence and uniqueness of this first order OD. Okay, so these solutions are like it's passing through 0, 1 and having slope c, and c is arbitrary, right? So I have this might be a potential solution, and this, like every curve, sorry, these are always going to pass through this point 0, 1. Okay, so let me ask the existence and uniqueness for this OD. Okay, so what are the x0 and y0? Like this is the initial value. That means y of x0 equal to y0. What are the x0 and y0 for which the solution exists and they're unique? Okay. For example, if you take any point here, right, you can always draw a line passing through these points, and that will be kind of the integral curve passing through that point, right? So any point on this plane, they're good, because if you pick any point here, let's say any point here, x0, y0, and then you can join these 2 points and get a line, and that will be a solution. Except, you know, this y-axis, except the point, you know, 0, 1. At these points, you cannot have any solution, because, you know, all these curves, they're kind of trying to reach to this y-axis, but they are not passing through this. So if you pick any points which is of the form 0, y0, such that y0 is not equal to 1. So for this set, you cannot guarantee the existence. So at these points, if you specify your initial condition at these points, you cannot guarantee the existence. In fact, there doesn't have any solution. Okay. Now, what about this point? This point is oversupplied, right? If you consider 0, 1, right? Passing through 0, 1, you have infinitely many solutions. So at this point, the uniqueness failed, right? Because you can draw many lines, and those are going to be solution for this particular ODs. So at this points, the existence fails, and here the uniqueness fails. So this OD doesn't guarantee, like it doesn't have existence and uniqueness. Is that a violation to existence and uniqueness theorem? No. Why? Because this OD doesn't satisfy the hypothesis for our existence and uniqueness theorem. And let us see why. So if you write down this equation in our standard form, so this is our f of x, y, right? And you can see this function is not even defined at x equal to 0. And x equal to 0 means, and y could be anything, right? So basically 0, y, at 0, y, such that y could be anything that belongs to R. At these points, this function is not even defined, so it's not continuous. So your existence and uniqueness theorem cannot guarantee anything, because f is not continuous. So you cannot draw any conclusion from existence and uniqueness theorem. In that sense, those are just sufficient condition. What I mean by that, if f and del f, del y are continuous, then you can guarantee that the solution exists and they're unique. But if some, if solution exists, or if f is not continuous, then you cannot say anything. Solution might exist, or there may be infinitely many solutions. Okay. I hope this is clear. Like the main point of this existence and uniqueness theorem, that they are actually sufficient condition, not necessary. Okay, so how much time do I have? Yeah, so I think I have 15 minutes from now. So I think I'm gonna, okay, let me just show very quickly. The next example, which is y prime equal to y into 1 minus y. This is a very special form of ODE, because if you see the right-hand side, this is a function of the independent, I mean, this is not a function of independent variable. This is a function that f only depends on the dependent variable y. And these are called autonomous system. And in applications, for example, population dynamics, or in counting some interest in a bank, this kind of ODE is used. Okay. So, and we want to know, and this has some special structure actually, because any line, any horizontal line, y equal to y naught, it's going to be an isocline with the slope f of y naught, and we can see that very easily. And because of that, the integral curves are always like, they are kind of parallel, so they're invariant under translation. And I think I'm going to skip this. I'll just show you by using this software developed by MIT how the solution looks. So let me just go back to, again, this nice software. So let me just use the equation y prime equal to y times a minus y. A is a parameter, so I'm going to choose a equal to 1. And let us just see how the direction field looks. Look at this. This is our direction field. And all these things, and this little line, this line, and this. So this is basically y equal to 0 and y equal to 1. Those are the critical points of this function, y times 1 minus y. And if you see the integral curve, these are the integral curves, and they're kind of trying to merge to this stable solution. And if you see integral curves here, they're also trying to merge. And that's why this is called stable solution. Y equal to 1 is stable critical point. What about y equal to 0? If you just see, the integral curves are moving away. So they're running away from the, this y equal to 0. That's why it's called unstable solution. Okay. So without even solving, you can see the family of integral curves, which are the solution to this differential equation. Okay. I wanted to talk about numerical methods, because in reality, you cannot solve all the time. In reality, you don't have even this right-hand side. Like here you have this well-defined right-hand side. This right-hand side might be some just numerical values. Sometimes you don't even get numerical values. So you don't have even information. So in that case, you have to solve this kind of differential equation numerically. Okay. And I will just demonstrate very basic, like the first numerical methods you will see if you take any numerical method course, which are known as Euler's method. Okay, so I'm going to present two Euler methods. One is called explicit, and another is implicit. Okay, and okay, so I need to use my notebook again. So how do you do? So let's say if you have a problem, y prime equal to f of xy, and you have also this initial value specified. Okay, and you want to know, because at this point, let's say this is your x naught and this is your y naught. So this is the information you already know, because this is given, right? So this is your y naught. This is my y-axis. This is my x-axis. Okay, this point is given. So if I want to know a solution at x1, and let's say this is my, let me use different notation for this. Let me use t, because these are basically used for time. So this is more realistic. So let me just t, and let's say t naught. Okay. So at t naught, you know the value, and you want to know the solution later time, and this, let's say this distance is delta t. So you want to know the solution at this point. How can you do this? Let's say your original solution, for example, passing through this point, looks like this. Okay, but you don't know this. I'm just assuming that you know for some ODEs. Okay. How do you calculate the solution at this point? Well, you can always draw the slope here, because you know these points. You know t naught and y naught. So if you know t naught and y naught, you know this function f, right? So if you calculate f of t naught y naught, this is the slope I know passing to this point, right? And if you just pick these points along this is an approximation to this solution at this point. So if you choose delta really close to this point, then you will be more accurate, right? So choosing the delta small, you can accurately actually approximate the true solution. And this is my so this is my solution. And how can you get this? So if you just form this triangle, you know this height is y0, and you know this slope, right? This is your f of t0 y0 from the given information, like the OD. And you know this length is delta t. So this length is going to be delta t times f of t0 y0. Okay, and this total length, let's say this is this total length is y1. So y1 is defined to be y0 plus this length. So y0 plus delta t times f of t0 and y0. Okay, so this is how you get this equation. So basically, these are just the numerical approximation to the original curve. Okay, now if you want to know at solution at t2, then you just use this previous information, and then you just calculate the slope, and this is the slope, and this will give you the solution at t2, and this is how you just iterate. So you basically get, so given the information at nth step, let's say you know the information at tn and the value is yn, then your next step, like at tn plus 1, you get the solution at tn plus 1 equal to yn plus delta t f of tn yn. And this is known as explicit Euler. There's a reason explicit. This is very important because you can actually determine everything from the previous step. So this slope, like you are calculating the slope here, that's why you know the slope. For example, if you want to use the slope like from here, basically tn and tn plus 1 and t and yn plus 1, you just take that slope and you just ad hocly use this here. You will get another method, which is just going to be, so instead of the slope at tn, you are using the slope from tn plus 1. And this is called implicit because in order to solve this, your nth, like your n plus 1th solution is involved to the right hand side. That's why this is called implicit. And this is explicit. And this is due to Euler. Okay, so these are two methods we can use to solve numerically. Now the problem is like how well these methods do, like to approximate this kind of OD. Okay, so and that leads to the study of accuracy, stability, then convergence. So these are all kind of stuff like you can learn in numerical methods for ODs or PDs. But let me tell you very quickly, like if this is a concave things, right? So if you use like forward Euler, which is explicit, you will always go high. If this is concave down, then it will always go down. And for the implicit, this is just opposite. Okay, so this is just the general information, like I'm giving this to you. And to talk about the accuracy of these methods, we know that this method is first order. Of course, I don't expect you to know these things. I'm just giving you the information. Okay, so let me go back to my slides again. So here I just listed these two methods, which is explicit and implicit, and you can see these are defined as yn plus 1. These are the numerical approximation at tn plus 1 is given by this formula, and implicit is given by this formula. So numerically, you can use this, or you can code this in a computer using MATLAB or Python or C or whatever you like, and you can get the numerical solution. Okay. And I already talked about this: accuracy, consistency, stability. These are very important for numerical methods, because if you are developing some numerical methods, you want to guarantee that your solution is reliable, right? And for those, you need to study all these features for a scheme. And okay, so let me skip that. Now let me give you an example, like how do you solve numerically? Okay, so this is a very special problem. It's called a Prothero-Robinson test problem. And you can see this is a very simple looking OD, but it's not. This OD is parameterized by two parameters. One is lambda, and another is this function phi of t. Okay, as you can see, if you just put u equal to phi t, this satisfies the equation. So phi t is a particular solution to this differential equation. In our numerical test case, we chose phi t equal to sine pi of t, and lambda equal to -2 and -20. This plays a crucial role, this parameter. So for lambda equal to -2 and for lambda equal to -20, the solution are completely different, and I'll show you in a minute. So look at this. So this is the solution corresponding to lambda equal to -2. So you remember u prime. So if you just go back, u prime. So let's say you don't have any of this, like any of these terms. So then you have like u prime equal to lambda u. That will give you the exponential solution with the exponent lambda, right? Now, if your lambda equal to -2, that is like exponential decay, right? And you can see all this. So these are the line elements I just talked about, right? And this directs the solution. And of course, our initial value is y0 equal to 0. That's why we see that this black line is the true solution. And these top two panels, they show the numerical solution by explicit Euler methods with 5 grid points and 10 grid points. So what are these grid points? So remember I talked about the delta t, and delta t is equal to 1 over this m. So of course, with m equal to 10, you have like smaller delta t, and that's why you have better approximation to the black curve. And this delta t is a little bigger. That's why you have this discrepancy here more compared to this. With the implicit Euler methods, you also see the numerical solution, and they're pretty much they're doing okay. They're not a great method because these are first order, and also these resolutions are really big, because in reality you take m equal to 100 or 1000 or even more, and then you see they exactly lie top of each other. So they approximate the true solution very well. Okay, so you see the direction fields are really, it's like really parallel, right? If you just draw all this integral curve, you can see that. And this is the simulation from my research, actually. So I work on this problem, and this is the simulation done by MATLAB. And let me show you other plots, which is corresponding to lambda equal to -20. Now, if you look at u prime equal to lambda u, right? Lambda was -20. So that curve is really decaying faster, right? Because the exponent is -20. And that's what you see from this integral curve. They're decaying really, really fast. Like they're almost like vertical, and then they're kind of trying to converge to this particular solution. Of course, they're not touching, they're not crossing. As I said, that is given by existence and uniqueness theorem, right? They're just kind of trying to approach to this stable solution, which is phi t equal to sine pi t. But the problem is, here this integral curves. Look, so if you start from here, you have a very short transition. Like the solution is coming here, and then suddenly it tries to approach to this solution. So this sudden transition is a very special fact, and it's called stiffness. Okay, and in reality, stiffness is a very hard problem. You can see this problem coming from chemical reaction or in heat equation, and those are very difficult to solve. And we don't have very good numerical methods to solve them. For example, if you try to use explicit Euler methods, you see you are already away. And if you just solve for more time, this will keep on oscillating and the oscillation will grow. So, this explicit methods are really bad to solve this stiff problem. So you have to always use implicit methods. And this implicit Euler is first order. And in my research, I want to we are trying to develop higher methods to solve this kind of stiff problem. Okay. So this is somehow connected. That's why I brought this like the first order OD thing and integral curve, so that I can talk to you about my research a little bit. And with that, I'll stop here. And thank you for your attention. If you have any questions, please feel free to ask me. I'll try to answer if I can. Thank you.
Thank you very much, sir. It was really a good explanation. Thank you for that. Now I request Dr. Deepsika of Mathematics Department Shyampur Siddheswari Mahavidyalaya, to take question answer session and further proceedings.
Thank you, sir, for such a nice presentation. Now we are going to start our question answer session. If anyone has any doubts, then please put your questions in the comment box. So, our first question is by Partho Sarkar. He wants to ask about the free availability of MATLAB. Is it freely available?
Usually it's given by your institute. If institute is not providing, you can always download a pirated version. So,
or you can use its options like Octave also.
Yeah.
Because it's an open software.
Yeah.
Okay. Now our next question is by Gopal Mandal. He is asking, what is the significance of delta t in implicit Euler method?
So in implicit Euler methods, you can actually take larger time steps, and that saves you a lot of computational cost. To understand these things, like, you have to really study the accuracy and the stability, because implicit function has unbounded region of stability. So you can take larger steps, and you can still get still good approximation. So that is the advantage over explicit methods.
Okay. Our next question is by Nirvik Masanta. He is asking, what is implicit Euler and explicit Euler method?
So as I mentioned, explicit Euler methods, so the next step, the current step, you can actually calculate the solution at the current step by using the previous information. But in implicit methods, you need the current information also, and that makes you like a little harder, because you have to use some Newton iteration methods in order to solve that, because that is like implicit equation, right? Yeah.
Okay, some people are asking about the availability of PPT. Means, can you share your PPT to them? So
okay, so I can so if you provide the email address, and I can give you my email address. So if you if you give my email address, then I can just send you that. It's not a problem.
Okay, sir will write his email address in the comment box. If someone wants PPT, then they can contact him.
Yeah, so I'll give it to you. Okay.
Okay, one more question is by Praveer Majumdar. He is asking, is this delta B a shift operator?
No. This means just a small portion. Like delta t is like 1/5 or 1/10. So it's just a small number. There's no operator involved here.
Okay. I think there is no other question. So
okay.
Let us all thank our speaker, Mr. Abhijit Biswas, for such a nice, informative, and enlightening session on differential equation. The geometric view of the differential equation was very nice. I think most of the students will get the deep understanding of differential equation, and they will learn the way to solve the equations in a different way. Thank you so much, sir, for joining us today in this webinar. Thanks a lot.
Thank you. Thank you very much.
Now we are going to start our next session. Our next speaker is Dr. Vikramaditya Sahu. Dr. Sahu completed his post-graduation in mathematics from Indian Institute of Technology, Bombay. After completing post-graduation, he did his doctorate degree from NISER Bhubaneswar. Then he went for postdoctoral studies in Indian Institute of Science, Bengaluru. Currently, Dr. Sahu is working on the post of assistant professor in Department of Mathematics, National Institute of Technology, Rourkela. His area of research interest include combinatoric geometry, it's algebraic combinatorics and finite geometry. He has many research publications in very reputed journals. Today, Dr. Sahu is going to deliver a talk on Jordan canonical form of matrices, and he is also going to show some of its applications in computer science. So let us all welcome Dr. Sahu to deliver his talk. Over to you, sir.
Thank you, Dr. Dipsika. Thank you for the introduction. So first of all, I'd like to thank organizing committee, organizers, Principal Dr. Bose, then all committee members, all advisors, all dignitaries who are associated with this webinar, all participants, everybody associated with this webinar. And I'm glad to be a part of this webinar. So my talk will be very basic. I'll give most of them are examples. I'll explain with examples. I'll give some application to computer science. So thank you everyone. So I'll start my lecture. Is it fine? Fine, right? Hello? Hello?
Sir, it's okay.
Yes, sir, it looks fine.
Carry on, carry on.
Okay. All right. Thank you. Okay. Good morning, everyone. So my title is Jordan canonical form of matrices, but don't afraid with this term. I'll start with very much basics of matrix theory. So before that, let us see something different. What is Google? So this Google is dominating the whole world nowadays. So actually, we should know something about this, right? The whole world is dominating this world. So these two persons, Sergey Brin and Larry Page, they actually invented this Google. When actually they were PhD student at the University of Stanford in 1998, in the Department of Computer Science. They were PhD student and they invented this Google in 1998. So see, they were like around like 24 or something. They invented this Google. So around 1998. And what they did, in the same year, they defined a matrix called Google matrix. This is a non-negative matrix of real numbers. And how they define? They define using link between two web pages. So the typical the matrix I cannot write here, but the matrix is real matrix, non-negative matrix, and it is defined using two web pages. If there is a link between them two web pages, then they define the matrix. They put some value and they define the matrix. And what is the one property is that one good property is that take a column of that matrix and sum it, then sum will be 1. Each column sum is 1. What is the use of this Google matrix? Then one can ask. So this Google is very much applicable in Perron-Frobenius theory. This is a very deep theory in matrix theory, whatever it is. This is used in our probability theory, Danical system, computer science, everywhere. So this Google matrix also related to Perron-Frobenius theories. In particular, all the eigenvalues of this Google matrix, modulus of these eigenvalues are lie between 0 to 1. So it lies inside a unit circle. It means mod of lambda is less than or equal to 1 for every eigenvalues. Using this Google matrix, what they did, this Sergey Brin and Larry Page, the word page rank is there. This is an algorithm. This is algorithm. But this page is because of this guy Larry Page, named after this guy Larry Page. It's page rank. This is an algorithm, and algorithms are all already used by computer scientists using mathematics tools, matrix to solve a system of linear equations. So in this algorithm, page rank algorithm, they use this Google matrix to find the rank of a web page in their search engine. Rank means that whether this web page is good or not. In their they define in page rank, they put a algorithm and they find some rank. So it is a way of measuring the importance of web pages. This is page rank. Page rank is just an algorithm. So for example, there are various research going on in this direction. So there is a paper on the Jordan canonical form of the Google matrix, a potential contribution to the page rank computation. This is published in a very nice journal, CM Journal of Mathematical Analysis Application. So this is about how this matrix is used, like in Google also matrix is using. We don't know that thing, but internally they are using matrix, linear algebra, matrix theory, everything inside, but that we don't know. We are thinking that mathematics is totally different from computer science, but computer science, they were the PhD student of computer science, and they invented this Google, and they use some matrix in their algorithm to find some link between some pages. So this is all about that one motivation I gave you. So let's start some basic mathematics. Why you study mathematics, this matrix theory and everything. So given a rectangular matrix means that may not be square matrix. We are taking only over reals or complex. This is a rectangular matrix. We say that rank of a matrix, or written as rank of a, is the number of linearly independent rows or column. Either takes number of linearly independent columns or rows. That many numbers are called the rank of the matrix. For example, this 3 by 3 identity matrix, this has rank 3 because there are 3 columns, and but also there are 3 rows. These are all linearly independent. Similarly, for this in particular, for a general diagonal matrix, this is called diagonal matrix because all other entries other than diagonals are 0. So this diagonal matrix is ranked the number of non-zero AIs. If A1, A2 are non-zero and A3 is 0, then rank is 2. So rank of this matrix is the number of non-zero AIs. Then one more important topic in matrix theory is the eigenvalue, eigenvectors. But eigenvalue is defined for a square matrix. There we can define rank for a rectangular matrix, but here eigenvalue is defined for a square matrix. We are taking over real or complex. The square matrix, we say that lambda is an eigenvalue if Ax equal to lambda x, where x is a vector in Rn, vector, and lambda is a scalar. Then we say that lambda is the eigenvalue of A and x is the eigenvector associated to lambda. If this satisfies, then we say that, sorry, actually eigenvalues are the roots of this polynomial called the characteristic polynomial. Take the matrix lambda I minus a, it is a n by n matrix, and take the determinant, it will be a polynomial of degree n over lambda, and take their roots, then it will be the all the roots are actually the eigenvalues of the matrix A. For example, I am taking very basic example always because to make you understand, everybody understand. Take this identity matrix, this 3 by 3 identity matrix, then lambda I minus I, take the determinant, and it will be lambda minus I cube, and only single eigenvalue with multiplicity 3, eigenvalue 1 with multiplicity 3. Similarly, if E1, E2, E3 are the vectors, these are think of this as column vectors 1 0 0 0 1 0 and 0 0 1. Then identity into EI equal to EI for each I. That means these EIs are eigenvectors with respect to the eigenvalue 1. There are three eigenvectors, but only one eigenvalue. Now consider this matrix, this upper triangular matrix. This looks like a triangle, right? If you are not taking this one, it looks like a triangle. This upper triangular matrix, below the diagonal all are 0. The eigenvalues are the diagonal elements. For an upper triangular matrix, eigenvalues are just the diagonal elements. But over R, any matrix may not have an eigenvalue. For example, this matrix 0 1 minus 1 0, this matrix, it doesn't have any eigenvalue over R because characteristic polynomial of this matrix is lambda square plus 1. But lambda square plus 1 doesn't have a root in over R. It has root over C plus minus I. I is square root of minus 1 is a root, but that is not in R. So this matrix doesn't have eigenvalue over R. Now, for some algorithm or something, we need matrix should be minimized. Like most of the entries should be 0 to make it clear and define it properly. A is similar to a matrix B if there is an invertible matrix Q such that Q inverse AQ equal to B. Then we say that A and B are similar. Suppose that this B is some nice matrix, nice in the sense that some very nice property is there, then we can study B instead of A, because they have similar same eigenvalues, they have same rank. So instead of studying this matrix A, we can study matrix about B. They they have same eigenvalue. The matrix A is said to be diagonalizable if A is similar to a diagonal matrix. If B is diagonal means all entries other than the diagonal entries are 0. Then we say that this matrix is diagonalizable if B is diagonal matrix. For example, all real symmetric matrices are diagonalizable. A matrix is diagonalizable if and only A has linearly independent eigenvectors. If a matrix has n linearly, where n is the order of the matrix, if they have the n linearly independent eigenvectors, that is diagonal. This is a very nice characterization of diagonalizable matrices. In fact, if A has n distinct eigenvalues, then they have n distinct linearly independent eigenvectors. So A is diagonalizable. So why we need diagonalization? Because if some matrix is diagonalizable, then it is similar to a diagonal matrix. That is more only that we can see only the diagonal entries, but other entries are 0. Consider this example. Lambda I minus A is this one. Then eigenvalues are the determinant of this matrix. Determinant of this matrix is, you can, it's an easy computation. You can compute lambda minus 1 square into lambda plus 2. So eigenvalues are 1 and minus 2. 1 with multiplicity 2. Now we can find eigenvectors also. If you put Ax equal to lambda x for lambda equal to 1, Ax equal to x, then we can find there are 3 linearly independent eigenvectors. This is column vector. Think of this as column vectors. Suppose consider this matrix, this eigenvector matrix. Like, put this first eigenvector in the first column, second eigenvector in the second column, and third eigenvector in the third column. This is called eigenvector matrix. And what we can see is that by easy computation, we can see that Q inverse AQ equal to D. D is this diagonal matrix. These diagonal elements are nothing but the eigenvalues. So what do we find? This matrix A is diagonalizable because this is similar to a diagonal matrix. Because we found this is invertible matrix, because these all are linearly independent. We found that Q inverse AQ equal to a diagonal matrix. So this matrix is diagonalizable. Can all matrices diagonalizable? No, not all matrices are diagonalizable, because if this were diagonalizable, then this has to similar to the matrix 0, because the diagonal entries should be the eigenvalues. Eigenvalues of this matrix are 0 and 0. So then if this matrix were diagonalizable, then A has to be 0, which is not possible. So this is not diagonalizable. So suppose a matrix is not diagonalizable, what we can do, we can decompose into some different matrix nearest to a diagonalizable. One thing is that all complex matrices are triangulable, means it is similar to a triangular matrix. If A is a complex matrix, then it is similar to a triangular matrix. There is a triangular matrix which is similar to A. But suppose a matrix is not diagonalizable, what we can do? We can make most of the entries 0. We try to make some like very simplest form, so that we can do some computation. We can find some eigenvalues, eigenvector rank. We can, looking at that similar matrix, we can find some properties of the matrix with that similarity property. So now this Jordan canonical form comes. Let A be a square matrix, then A is similar to a matrix J of the form called the Jordan canonical form. Any matrix is similar to a matrix of this form. Any matrix is similar to a matrix of this form. These Ji's are not entries, real numbers or complex number, but any matrix over C I am saying here, not over R. Any matrix is similar to a matrix of this form. J1, J2 are actually small matrices of small order. These are not entries. Suppose this in the case of diagonalizable matrix, these all are entries. All entries are numbers. But here these GIs are not numbers, may not be numbers. So any matrix is similar to a matrix of this form. This is called Jordan canonical form of A. And this number of these GIs are the number of linearly independent eigenvector of A. If it has S linearly independent eigenvector, then there are JS. And what about the order of this J1? Suppose how this Ji looks? Ji is an upper triangular matrix with all diagonal entries single eigenvalue. Above the diagonal entries all ones and others 0. This is an upper triangular matrix. This all Ji's are some eigenvalue diagonal matrix with diagonal entries lambda i's, single lambda i's, and all above the diagonal ones and all 0. And this this single Ji is called a Jordan block belonging to the eigenvalue lambda I. And one can say, what is the order of this matrix Ji? The order is the smallest k such that J minus lambda I to the power k is equal to 0. The order of this matrix Ji is the smallest k such that k equal to 0. This power equal to 0. So why we want a matrix to be like Jordan canonical form? Because if you want to find some properties of this matrix A, by looking at this Jordan canonical form, we can say about A also, because this is a very nice matrix. For example, you can say rank, determinant, and what is the minimal polynomial, characteristic polynomial, eigenvalues, everything we can say by looking at the Jordan form of this matrix A. So, for example, consider this example. So there are two eigenvalues, 2 and 3. 2 is multiplicity 2, but 3 is single. So there are two eigenvalues. So what is the Jordan canonical form says that the number of Jordan block is same as the number of linearly independent eigenvector. In our example, there are two eigenvalues, so at least there are two linearly independent eigenvector. So in that case, there are two eigenvalues with 2 repeated. So there are at least two linearly independent eigenvector, but either 2 or 3 eigenvector. So in that case, there are two possibilities of the Jordan canonical form of A. Either this one, in that case, there are 3 linearly independent eigenvector, or in this case, there are 2 linearly independent eigenvector, because there are two Jordan block. This one is one Jordan block. This one is one single Jordan block. This is single Jordan block, that's containing 2 only. And this is also 3 Jordan block. So depending upon the number of linearly independent eigenvector, we can find there are two possibilities. But the thing is, rank of A minus 2i, if you take rank of A minus 2i is 2, which is same as rank of the Jordan matrix, Jordan canonical form. But here rank of J minus 2i is only 1, because this will be 0, 0, rank of J minus 2i. But rank should be same. So this will be the Jordan canonical form of this matrix A. So we found that Jordan canonical form of a matrix. Then how can we find this Q matrix, the change of basis matrix Q? This this matrix was given, and we found that the Jordan canonical form is this one. By comparing this equation AQ equal to QJ, this one AQ, by this equation, we can see that AQ equal to QJ. So by putting here AQ equal to QJ and do some computation, we can find that Q is these are column vectors. X1 is a column vector, X2 is a column vector, X3 is a column vector, because this is a matrix. But we get that AX1 equal to 2x1, AX2 equal to 2x2 plus x1, this one. But this means that x1 is a eigenvector with respect to the eigenvalue 2, and x3 is also an eigenvector with respect to the eigenvalue 3. So we can take any eigenvector and put it here for x1, and x3 take any eigenvector, put it here, and solve for this equation. You get this matrix Q. Any constant will work for this matrix Q. So we found for an example, we found both the Jordan canonical form matrix and the matrix basis matrix Q. So there are various applications of this Jordan canonical form Particularly in mathematics, we can prove Cayley-Hamilton theorem. What is that? Cayley-Hamilton theorem? Any matrix satisfies its characteristic polynomial. You can prove Cayley-Hamilton theorem. This is a very important theorem in mathematics. You can prove in differential equation. It is used in differential equation. In fact, you can find the minimal polynomial of A. Minimal polynomial of a matrix is the minimum degree polynomial satisfied by that matrix. And we can find the power of any power of that matrix, in particular any e to the power A, and we can solve differential equation. This is the application of Jordan canonical form in mathematics. different areas of mathematics. Now we will give one beautiful application of this matrix theory in computer science. How the computer scientists used matrix decomposition in their algorithm. For that, let us define what is singular value decomposition. Consider A be a rectangular matrix of size m by n, real matrix. Then A can be decomposed as U into sigma into V transpose. This is transpose of the matrix V, where U and V are orthogonal matrices. Orthogonal means U into U transpose equal to identity and V into V transpose equal to n. If somebody don't understand orthogonal, just think about A can be written as some product of three matrices. Don't confuse it orthogonal and everything. Just think of this: A is written as product of three matrices. So don't be confused with that. Just I want to give you an application, very beautiful application of singular value decomposition. So this U is an orthogonal matrix, M by n orthogonal matrix, V is an n by n orthogonal matrix, and sigma with a diagonal matrix. Rectangular diagonal entries with non-negative. Entries are non-negative. The diagonal entries are non-negative. So we say that the diagonal entries of this sigma matrix is called singular values of A. That's why singular value decomposition. And the columns or V are called right singular vectors. Column of this right matrix, columns of this right matrix are called singular value right singular vectors. And columns of this matrix U are called left singular vectors. And this decomposition A equal to U sigma V transpose is called the singular value decomposition. In short, people use SVD, singular value decomposition. There are numerous applications of singular value decomposition. For example, it is used in computer science, this Markov chain, probability theory, stochastic process, everything. We use singular value. People are using nowadays. There is a great deal of research in this direction, singular value decomposition. So, in particular, we'll give one application of this to computer science. How this computer scientists use this in image processing. How this decomposition of matrix they used. Numbers in a matrix might represent data or mathematical equation. People solve a system of linear equation using in their algorithm. So they use matrix theory. So numbers in a matrix might represent some data. So matrix contains some number, real matrices, some contains a number. So what computer scientists does, they actually take number as some data in their some algorithm. They put some data in the matrix and they put in their algorithm that matrix, then so that we can get some quick applications on some complicated calculation. So that's why matrix theory is very much important in computer science. Matrices were originally devised as a way of describing system of linear equation. Given system, people use system of linear equation and they want to solve this system of linear equation. Then what they do, they put in matrix form and then they put in some algorithm, they get some complicated calculation. Then in putting in that algorithm, they get very easy, like quick result they get, approximation at least. And matrix multiplication is particularly useful in graphics. Since a digital image is basically a matrix to begin with, rows and columns. Suppose some image is there, like in my video, suppose we are playing video, right? So suppose some very, like, we need some more data, right? To make it compressed, what we do, we cannot send this original image, right? We have to compress it. Otherwise, you cannot keep this much data in some computer or something. So what they do, that take a picture, they take a, suppose some picture is there, then take one pixel, that pixel is some color values is there, then put in some matrix form, so that matrix form, then they will get a real matrix. Pixel values are just number, color values. So what they do actually, and some nearby pixels are related, then image can be compressed. Actually, what they do, suppose some picture is there, 1000 by 1000 by 1000 area of pixel. Put in pixel because that one single value represents single color pixel, color value. So one number, this 1 million numbers represent 1 million pixel value. So this can be thought of as a 1000 by 1000 matrix of real numbers represent colors. So what they do, they cannot send this much value, right? They cannot put in some algorithm or some software, because this is very 1 million thing, 1000 into 1000, 1 million. So what this does, this matrix theory, this is a matrix, is nothing but a matrix, right? There is a decomposition of this matrix, A equal to U sigma V transpose, and A can also be written as sum of rank 1 matrices. This U1 UI Vi transpose, these are rank 1 matrices. This is rank 1 matrices. This sigma 1 are singular values, sigma 1 U1, there are suppose R singular values, non-zero singular values, then A can be written as R singular values. And if we take 20 singular values, suppose sigma is that there are 20 numbers, instead of sending this 1 million numbers, there are 1 million number, right? That 1000 by 1000 matrix contain 1 million numbers. Instead of sending 1 million numbers, see this decomposition. We are applying this singular value decomposition of this matrix. So consider this decomposition. There are, this one is 20 numbers, sigma is at 20, and this UI this contains 1000 and this contains 1000. There are 2000. Similarly, this at 2000. So 20 into 2000. So we send only 40,000 numbers rather than a million numbers. This is million, 1 million, right? So we are sending only 20,000. So this can be, this represents a compression of 25:1. We can compress this image by, we are not sending the 1 million entries. We are just sending just 40,000 numbers. So we'll compression of 25:1 compression. So this is a very nice application of the singular value decomposition in image processing. How to compress image in, so that's why this is very, this decomposition of matrix is very much important in computer science as well as probability theory everywhere. So I gave only 2 examples, so there are more examples, so I'll stop here. So any question?
So if anyone has any question, then they can ask their doubts in the chat box. I think we have no question. So thank you so much, Dr. Sahu, for such a wonderful and enlightening talk on Jordan canonical forms of matrices. As we know, Google is used by everyone nowadays, and it's a need of everyone. So it was wonderful to know how matrices and mathematics play a crucial role in search engine like Google. I hope all the participants get benefited from this. Thank you so much for joining us today in this webinar. Thanks a lot.
Thank you everyone.
Okay, we have few more questions for Mr. Abhijit Biswas. So I'm going to ask those questions to sir.
Yeah.
Okay, just a second.
Sure, no problem.
Okay. So first question is by Nirvik Masanta. He is asking, is there any errors in this method? If yes, how you tackle the errors obtained by this methods? Means the Euler implicit Euler and explicit Euler methods. You want to?
Okay, so let me share my screen and show you the last slides. I hope you can see my screen, right?
Yes, yes.
Yeah, so here if you see, let me just go back to one more slide. So here you can see, this red curve, this represents the numerical solution by explicit Euler with few number of grid points. And you can see this is, there's a gap between this, right? And that is the error. So let's say the numerical error is, so the numerical error is defined to be the difference between these two curves at any given time. Okay, so it's basically the absolute value of the numerical solution and the true solution. There's a way to quantify this in terms of local transition error, and that is defined actually to be the true solution at the time and the numerical solution. And you can quantify that by using Taylor series expansion. And if you do for these methods, you will see this is something called first order accurate. And what I mean by that is, like, if you decrease your delta t by half, then your error will also decrease by half. For example, in this case, my m equal to 5, right? So delta t is 1/5. And in this case, my delta t is 1/10. So I'm going from 1/5 to 1/10. So my error also decreased by half. You can see visually, right? So that is what I mean by the error is first order. That means the error behaves almost like proportionally to delta t, and this is known as first order. And if you just do Taylor series expansion, you can see that easily. Okay, so yeah, there is a way to quantify errors. Yes.
Okay, next question is by Biswajit Das. He is asking implicit or explicit, which is more accurate?
Okay, so these two methods are first order accurate, so there is no like better methods. But of course, implicit has this advantage over explicit, is that implicit has unbounded domain of stability region, which means you can take delta t as large as you can, like as you want. That's the advantage. Because just think about this problem. If you take delta t very small, right, then you have to do all this evaluation of function, and that is like calculated at the computational cost. So you don't want to compute at many points. You want to compute on a fewer number of points, and still you want to get a nice solution, right? And if you see like this method, like with even m equal to 5, the solution is unstable. Unstable means the solution is growing and it's becoming unbounded. So explicit methods fails here, but implicit method still works. That's because with even this larger, delta t, this works and the method is guaranteed to be stable. So that is the advantage of implicit methods over explicit methods. Yeah, but the accuracy, both are same within the within the domain of stability region. Yeah.
Okay, next question is by Sukanto Samanta. He is asking, can we use these techniques for partial differential equations?
Oh yeah, absolutely. Like these things are developed for partial differential equations. For example, if you have heat equation, then you have ut equal to uxx. What you do, uxx, like you approximate that uxx by a system. So your right hand side now becomes a system. So here we have just a single variable. So there we'll have multiple variables, and that will be a system of differential equation. And you actually solve these things by using numerical methods, for example, implicit Euler or explicit Euler. Of course, in reality, you want to use more accurate methods, which I didn't talk about here. Yeah.
Okay, sir. Next question is by Milan Bagh. He's asking some kind of special type of differential equations like Legendre differential equation, Hermite and Bessel equation. Can these type of equation be solved by the numerical methods?
So if I remember these equations correctly, these all are second order differential equations, right? So there is one independent variable and one dependent variable and y depends on x, but this is a second order differential equation. So what you can do is like any nth degree differential equation you can write down as a system of differential equation. So if you have second order differential equation, you can write that as a system of 2 by 2, like you introduce a little variable x1 and x2, and you can write down these equations as system of differential equations. Then this becomes a first order system, right? And exactly, you can use this methods, for example, implicit and explicit Euler to solve that system. Once you get the solution, then you just use your solution, the formula to get back to your original variable y. You can solve these equations also.
I think there is no other question. So thank you so much, Mr. Abhijit Biswas, once again for giving us your valuable time. Thanks a lot.
Thank you. No problem. Bye. So I think we
Yes, you want to say something?
I mean, are we going just offline from this or what? Is there anything?
No, we are going for both of hands and then we will go offline.
Okay.
Okay. So now I would like to request Professor Mridul Ghosh to deliver the vote of thanks.
So we are on the verge of our international seminar. It was really a nice seminar. On behalf of the departments of mathematics and computer science, I am thankful to Mr. Abhijit Biswas and Dr. Vikramaditya Sahu for their wonderful speech by blending mathematics and computer science. I am thankful to our honorable principal sir, Dr. S.K. Bose, and our honorable president, Sri Kalipada Mondol, for their support and encouragement. I'm thankful to the GB members of our college for encouraging us. I'm thankful to the IQAC coordinator, Sri Rajor Simfarji, and the members of the IQAC. I'm thankful to the head of the Department of Mathematics, Dr. Arun Kumar Maiti, and Dr. Deepsika. I'm thankful to Mr. Snehendu Mondol and Ms. Rini Maiti from the Department of Mathematics, and Mrs. Ondamunna Roy from Commerce Department, and Mrs. Shatabdi Khara and Olagananda Bodal from Computer Science Department for their constant support. Last but not the least, I'm thankful to Mr. Surajit Mondol, Head of the Department of Physics, Mr. Prosenjit Don, Assistant Professor of Zoology, and Mr. Somen Teli, Assistant Professor in Library, for their constant technical support. Thank you all, be safe and stay healthy and have a good day. We are signing off.